Okay, so hello everyone. Thanks for joining us another day. So today is day 3 of the DeSIRe tutorial. As you can see, my voice is even worse than 2 weeks ago. So last Friday it was terrible and I'm recovering, but still I'm fluctuating. So I will try to make it until the end, and I'm apologizing for my voice because I know it's terrible. But still, let's try. Okay, so then today's course I think is going to be very interesting because we are going to learn to do something that you probably will do eventually, that is performing synthesis with DeSIRe. We want to show you how to do it in a different way. So we will start with a very simple LTE case that it should be similar to what you do with SER. But then we will start adding non-LTE lines, and then we will also add LTE satellite lines that are going to be in the wings of those non-LTE lines. So this will be a very complete exercise. The idea is that it's also, I think, helpful because we are going to focus on the calcium 2 infrared lines, 8498 and 8542. And those are the lines that are going to be first observed by the first observations of the keys with WISP. And also the instrument SKIP on board of Sunrise that is going to fly this summer is going to observe those transitions. So they are transitions that we are going to have access this year to them. So it's good that we learn how to include not only the calcium lines, but also satellite lines that are going to be helpful for constraining a bit better the atmospheric parameters. Okay. So we will do the test, and also at the end we will make a quick check where we synthesize those profiles with a standard white sand atmosphere, and we compare that with the atlas. So we will do first an exercise of how to synthesize and include lines, and then we will compare those profiles with the atlas just to check if the atomic parameters that we define are reasonable. Okay. So then in this section, there's nothing today. That is good. And then we will go back to homework later on. So then just let me minimize this. And then the idea is that we are going to work today in 4 different folders. I will show you later, but the idea is that I will share with you this day 3 run 1, 2, 3, and 4. Okay. And I separated them for keeping things clear, and I will show you later why I prefer it this way. So then let's start with the first one. So here you will have this run.pro, this ideal procedure, that is this one that we have here. So then let's start with this, and then we will check why I prefer to separate it in different folders. Okay, so as I said, we want to synthesize non-LTE spectral lines, or spectral lines assuming non-LTE, transitions that are mainly photospheric, so they behave well under LTE. But inside those group of LTE lines, we will synthesize lines that are well described under the LS coupling, but also we will include JJ and J1K coupling schemes. Okay, or JK, you can say it this way, probably it's easier. So then the first thing we need for doing synthesis, we need always multiple files, but the first thing you need is the atmosphere. So if you remember, in the last class, I showed you a very simple example with HSRA atmosphere, and I put it constant magnetic field and velocity in that case. I think in this case, I wanted to make things a bit more interesting. So I'm adding this time to the same HSRA atmosphere, I'm adding gradients, linear ones, but I'm adding gradients. So then in this case, I'm not touching the temperature because for this simple example, it's probably fine. Then I'm putting just microturbulence just for adding a value, but you can keep it to 0 or add a different value. And then this instruction, as you will say later, is in ideal, it will allow you to compute a linear gradient for magnetic field strength. I'm doing the same for velocity and the same for inclination. Okay, so then I'm writing, and the azimuth is constant just to keep things simple. And then I'm writing the atmosphere here, and I'm making a plot here. So let me show you how the plot looks. make it a bit bigger. So then we have that the temperature is the same one, so it's fine. Then the microturbulence is constant. And then the velocity, I just said, okay, let's put a velocity that is increasing with height, and it's a reasonable value. So you have around log tau -5 is around 6 kilometers per second. And in the photosphere is around 2.5 kilometers per second. So it's a high velocity, but it's something that is not really crazy, let's say it this way. Then I'm doing the same with the magnetic field. I'm putting a gradient, but to try to keep things simple, and the gradient is decreasing with height. So you imagine that you have a magnetic field that is strong in the photosphere and is expanding with height. So then you can assume that it could be something like this. So you have like 1 kilogauss in the very bottom of the photosphere, and then it's decreasing up to around 400 gauss around log tau -5. So something reasonable. And that magnetic field is not only decreasing in strength, but also is getting a bit more inclined. So imagine like you have the magnetic field that is opening with height. How fast it will open, I don't know. And so in this case, I just put it as an example, this decrease. So it goes from almost vertical in log tau 0 to 50 degrees. Okay, and the azimuth is constant with height. So the purpose of this atmosphere is to synthesize the profiles, but also show you that if you have gradients in the line of sight velocity and the magnetic field, you will have asymmetries in the Stokes profile. So it's just to give you also some flavor of how different atmospheres can impact on the spectral signatures that you have in your profiles. Okay, so then with that, now we are going to do a synthesis. Okay. So then the first thing that you want to define when you do a synthesis is the lines you want to synthesize. So as I said, we plan to synthesize calcium 8498, 8542. So these are the non-LTE lines. But also we want to complement them with the traditional iron lines at 630 nanometers. So my impression is that it was better to just go step by step. So what we're going to do is first, we are going to synthesize only the iron lines. And then I said to try to avoid changing the files on the go, we are going to create a line file or a grid file for telling the code which lines we want to synthesize in 3 different folders. So in the first folder, we only call to the iron lines. In the second folder, we add to the iron lines only the calcium lines. And in the third folder, we are going to have the iron lines at 330 nanometers, the calcium lines, the infrared ones, and then additional satellite lines that are in the wings of the calcium line. So then step by step, we are going to increase the complexity of the synthesis, and I separated them in folders, so then it's easy for you to compare one and the other case. Okay, so then we will have essentially to create 3 grid files that I called wave 1, 2, and 3, and they are included in those folders. Okay, there are minor changes that I added, so I will comment them here, but essentially most of the files are going to be the same. Okay, so then when you are going to synthesize LTE lines, you need to go to the lines file. In this case, it's called lines non-LTE. It's the same that you have in the examples. I mean, the name is the same, but I changed it. So then you go to the one, it's an input, and then you double click there, and this one, okay? Yes, this one, yes. So I think this was, sorry, these are old ones. So then, as I said, we want to synthesize first the iron lines at 630 nanometers, and you can see that index 1 and index 2 are the 2 lines that we want. So then our wave grid file is this one. So then we want to have these 2 indexes here, 1 and 2. Remember that you can separate them, 1 and 2, but usually we observe them always together. So then the best thing is just to put 1 and 2 together like they were a blend, and then have a spectral range that cover both lines. And again, as I said in the previous class, this spectral range is always referred to the first index that you have here. So then you are saying that you are starting at minus 700 milliangstrom from the iron 6301.5 angstrom transition, and then you are ending at 1800 milliangstrom from that transition. Taking into account that the difference between 1 and 2, you can see here, is essentially 1 angstrom, then what we are saying is that we are living around sorry, 500 milliangstrom, I think 500 milliangstrom to the right side of the iron line. So then we are just giving enough space for the second line, but it's always referred to the, sorry, we are leaving 800 milliangstrom of space to the right side of the iron 6302.5 line. Okay. So then with that, then we want to run the synthesis, and then we have configured the grid file. And then in this case, as we are only going to synthesize LTE lines, you can set as passive the atoms in the atoms.input. So if you go here, so in this case, I have it as passive. I'm specifying that the atom is here, but I'm leaving it as passive because in this case, it's not necessary. We are going to add it later. So my goal here was to show you what things you need to change when you are going to do a non-LTE synthesis, mainly if you come from SER and you want to know what things you need to change. Okay, so then with that done, we need to call DeSIRe. In this case, we are going to call synthesis.dtroll. So then we go back, we open this file, and we double check that we are calling the proper wave grid file that we are defining, that is here, you can see. Also the lines file is the same. And then the abundance we didn't change it. And then the atmosphere, I probably didn't mention, but when I create the atmosphere, I save it with this name. So then we are verifying that we are calling the atmosphere we want to choose, okay? And then with that, essentially, we are ready for running the code. Let me see if we are, yes. So then we just run the code, and then it was very quick because it's an LTE computation, and then the code worked. And I'm saving, so I'm reading the profiles here as we did last week. If you remember last week, again, we looked for the index, the first index in the grid file, and then we picked only the pixels that contain that index in the full array of synthesis. In this case, it's only iron line, but later on we will have different lines. And then we created a new wavelength vector that now is the reference of this wavelength vector is the line center, the absolute line center of the iron line, because usually we give it in respect to the center and normalize, so it's always plus minus 1 angstrom or something like that. But now it's going to be the absolute wavelength value. Okay, and then I plot Stokes I, Q, U, and V with this new wavelength vector. And then we can see that here. Okay. As always, I'm putting, just let me go back. As always, in the folder day 3 that I will share with you, there's HD figures, and there are all the figures that I'm showing you, they are there as well. So you will be able to select them just and check them here. Okay. So then let's go back here. So we have the two iron lines, so 6301.5, 6302.5. If we focus on Stokes I, we see that they are redshifted to respect to the rest line center. This is because we put it a positive velocity, so it means a downflow. But then if you look at the Stokes profiles, for example, Q and U, you will see that the shape, there's always one lobe that is larger than the other, and this is because of the gradients along the line of sight. And the same happens with Stokes V. So you have that this lobe is it has a larger amplitude than this one, in absolute value than this one, and the same here. And probably if we compute the area, so below this lobe and below this lobe is also going to be different. Okay, so having gradients along the line of sight will always produce this type of shapes. Okay. So then this was the first case. If there's no questions, I will go to the second one. If there's any, just please let me know. So I will.
Yeah, I have a question, Carlos. So
Yes.
in this atoms dot input, or you just closed it?
Yeah,
Yes.
no, I will open again. So don't worry.
Yeah.
Yes.
So here, when we are doing LTE inversions, all atoms has to be in passive. Am I correct?
Yes. So I think it's not has to be. So I mean, if you have it inactive, the code will solve the atom and it will not use the information. So you are making the process slower, but not inaccurate. But if you make it passive, then you will have the same results, but it will be faster as well.
Okay, so here I also see, like, for example, for iron atom, it's passive, and it's also written that it's LTE population. So if I, for example, make it active to synthesize these iron lines, still it will take LTE populations.
No,
Okay.
no. So these atoms, they are computing non-LTE population. So if you have iron atom as an active atom, then you are trying to solve the photospheric lines, for example, in non-LTE. That this is something that is, I think, maybe overkill. So
okay.
So,
Oh, that's the initial solution. Okay, it will start with the LTE.
Yes,
okay. Yeah,
yes. LTE population is the initial solution for the
Okay,
non-LTE
yes.
problem.
Okay, I understand now.
But when solving LTE lines, so for example, when solving the iron lines, we don't solve actively the iron atom because we compute the populations through the Saha-Boltzmann equation, assuming LTE, and then those atoms are not always, they are always passive. Okay.
Yes. Okay. Yes.
So let's say in another way. So you have to put active only in the transitions or the atoms that contain transitions that you want to solve in non-LTE. So calcium, imagine magnesium 2, imagine H alpha. So then you have to put those atoms. But the rest of transitions, so imagine that you have silicon 1, I don't know, carbon 1, but they are photospheric lines, then everything should be passive.
Okay. Yes. Yeah.
I think Han, you want to add?
Yeah, I think it's also important to note or realize that in this case, in this calculation, the iron lines are, as you specify them in the atoms. So the iron lines that you calculate are not from this atom.
Yes.
Right, to specify them as LTE lines separately.
Yes, they are from here, from this computation.
Yeah.
Yes.
So here what we are doing is that even for the calcium computation, you want to have the background opacities with high accuracy. So we are taking into account all these atoms for computing the background opacities. But for solving specific lines, like for example, the iron 1, let's say index 1 and index 2, we are using this information that you see here.
Yeah.
Okay.
Yeah. Okay.
Thanks. Now we are going to perform the calcium computation, and I think you will probably understand a bit better. But if not, we can revise it at the end. Okay. So then.
Okay.
Okay. So then let me go back to this point. So then, this first part is the same. So we just skip until I think I put new. So then. In this case, we are going to add the calcium 8498 and 8542, and the computation is the same as before, but we are going to change the grid file. So here I said, again, please be aware that in synthesis.roll, so now everything is the same except this one, okay? That is, now it's wave2.grid. And then the idea is what we need to check now. So the index of the non-LTE lines should be included. So then we go to the lines non-LTE file, and then we said, okay, the calcium 8498 and 8542, they are index 3 and 4. In this case, they are separated around, I think, almost 40 or more than 40 angstrom. So then it doesn't make sense to have them as blended. So then we have to put 2 entrants. So in this case, it will be like this. So it will be the 2 lines that we have from before, and now we have 3 and 4. Okay. So now we have the index. Then I put another thing that you need to check is now your atom active? So then we have to go to atoms.input and verify that we are asking the code to solve the atom in NLTE. So actively compute populations that we will use later for computing the departure coefficients. Okay. And then this is very important. So are the indexes of the elements that you see in the lines file the same, and they correspond to the levels in the atom? So then let me explain what I mean. So I think I mentioned this, but I wanted to emphasize it again. So if you see there, for example, for the iron line, this one or this silicon one, so you have multiple columns, but at the end, they all finish with these values that are up to the -13, -14. And this is the enhancement, I think sigma or alpha, I don't remember the one, but it's the collisions with hydrogen. But then you have, for these 2 transitions, you have 2 numbers. And these are the lower and the upper level of the transitions that are defined in the atom. So then you have to really check these 2 numbers and verify that in the atom that you are solving as active. So let's go back. And I'm saying in this folder, that is the one we have calcium 2 CAT.atom. So we have this one. We open it. And then we said, okay, the calcium 8498 transition is a transition that goes from level 1 to level 4 in this atom. Okay. So then in lines NLTE, we have here that 8498 also goes from level 1 to level 4. Okay. So then this is consistent. If you change of atom, because you are creating a new one, or someone send you one that is more complex and is probably more accurate, you have to update these values, because probably you will have more levels, and then the transitions between levels, they will have a different index, and then you have to update it here. If you're using the same one, it's always fine, but just to be aware of that. So changing atoms will probably change the levels and the index of the levels involved in the transition. So then you need to change, to update it here. So then just as a double check, so 8542, it goes from level 2, is a lower level, and to level 4. And we go here, and then we have here level 2 and level 4. Okay, so things are compatible. So we have an active atom, and the transitions that we have in the lines file are compatible with the levels of the active atom. And then here is just configure the grid file to cover both transitions. And if you see here, we started from 700 in the case of iron lines, so probably with -500 to 500 milliamps. Usually you can cover a photospheric line, but for chromospheric lines, you have to make the range much broader. In this case, I went for 6,000 in both cases, and in the case of calcium, I went a bit more in this case, because there are some interesting lines that we have in the right side that I wanted to include. So you can see that it's almost 10 times larger, because they are much broader. Just for simplifying things, I change the step and I make it a bit bigger, but it's just for having lower values. But you can put here also 10, it's also fine. And for example, when you have high resolution, high spectral resolution from VISP, I think this number is going to be much smaller, sometimes 5 milliamps or something like that. So we can play with this value. So then we have everything. Then we run the code again. We read the profiles. The first part is the same. So we have again index 1 for the iron lines, and then I just do the same, but now we enter with the calcium lines. So then if you remember, we go to the grid file, we have one entrance that is 3 and a second entrance that is 4. So then we read line 3, we checked that in lines non-LTE, this is the wavelength region. So then we can compute our wavelength vector with respect to the absolute value. And then we do the same for the calcium 8542. So we read index 4, and then we put our wavelength in absolute value in nanometers. And then we just make the plot. So in this case, is 8498. So Stokes I, Q, U, and B. And then the same for 8542, I, Q, U, and B. Okay, so then let's check the figures. So we have 8498, that it looks like this. So you have that the line is broad. There's some thing here that I believe is just an effect of the gradient. Then Stokes Q and U signals are weak because it's a chromospheric line, and also the lambda factor is much smaller than the iron lines. And the shape is a bit complex. And in fact, in the Stokes B, it's even more complex because we have chromospheric lines that they are usually complex, but also we have a gradient along the line of sight. So we have these wings that are smooth, then we should have like a normal one, but now we have this peak that probably is an effect that we see here. Okay. And then if we go to the 8542, we have something similar, but not the same. So we have this effect here. Then here it doesn't seem to be so abrupt as before. And then in this case, also although we have this peak, in the previous one, this side was larger than this one. So then for me, this is always interesting because it means that the lines, they are probably not, they are not seeing the event in the same way, maybe because they form in a different height, maybe because they have different sensitivity to the atmospheric parameters, or both. So then in summary, combining these two lines is helpful because they are going to provide probably complementary information that you cannot have with just one line. So then I think this is a good thing. Okay, so then at this point, now we are going to increase the complexity. So just to recap, what we did is we start from the previous one. We set the atom as active. We put those index in the wave grid file, and then we run the synthesis and we compute it. Now lines in LTE and lines in non-LTE. Okay, so then I go to, just ask me any question, please, if you have now, and if not, I will continue with the last example.
Very simple question.
Yeah, Ryan, yeah, go ahead, please.
In the lines NLTE file, where you identify the lower and the upper level for the active transitions, you have to have the full stop. Is that important?
Full stop. You mean this comment here?
Yeah. No. So you see how there's a dot? Does that have to be there?
No. I think no, Basilio, right?
I was muted.
Yes.
No, it's not needed.
Yes. I think levels are not real numbers.
Yeah.
Yes.
You can put an integer number.
Yes. Yeah, thanks, Ryan. That's a good question. Yeah, usually we don't have 4.5 levels or something like that. Okay. So then, just let me. So is this yes? This is number 3. So then again, the first part is the same. It's just because I wanted to have separate as a standalone, so you can work with one. You don't need to bring files from the other. So then the first part is the same. We create atmosphere and we plot it. And then now this part is new, and we have photospheric lines in 630 nanometers, the calcium lines in the infrared. So now let's add satellite lines in the wings of the calcium lines. Okay. So then we have that now wave is wave 3. So you go to the synthesis.roll, and then this is the only change that we have here. So it's wave 3. And then the idea is we check the same things as before. So the index should be included in the grid file. Let's see here. So now it's a bit different. I will explain it in just 1 second, but just verify that the atom is active. So then we have it here. So we can just close it just to avoid mixing a lot of things. Oh, sorry. Yes, and And just be sure, in this case, we are not changing the atom, so it doesn't matter if you were pointing to the atom in the first folder, but just to keep things consistent, I was changing this path. And sometimes you may change a bit one atom to the or other. So just be sure that we are pointing to the atom that you actually want to use, because they could be the same, but just with minor modifications, and then you don't realize that you are using the old one. And then, yes, this we did it again. And then now we are going to configure the wavefleet file. So then the idea is that if we go to lines in NLTE and we check index 5, 6, 7, and 8, we see that they are very close to 8498. Okay, so this is a calcium line. So then we have 8496 that is in the blue wing of the calcium line, and then 501, 501, and 502. So we have lines that are in the red wing of the calcium line. Okay, so then we want to include all those lines number. So index 5, 6, 7, and 8. Okay, but you have two ways of doing this. One way is to put the lines organized in wavelength. So then it means that the first entrance should be 5 because it's 8496. Then it will be 3 because it's 8498. And then it will be 6, 7, 8, and that's all. But another way is to just keep the calcium line as the first index. And this is because, as I said before, the spectral range that you define here is going to be referred to the first index. So if you want to cover the calcium line symmetrically and just add things somewhere close to the core or farther, the best thing you can do is just keep the calcium line as a first index. So then you will have a symmetric spectral range from -6000 to 6000. And then you can add any line here or remove it. And it doesn't matter if you add it or remove them, you always have your spectral range referred to the core of the calcium line. If you do the opposite, so if you put, for example, index 5, then you have your spectral range shifted to the calcium line. And then if you change that line, then everything will be shifted. So my advice, it's not mandatory, but my advice is that with these big lines, just put the line you are interested most, the first index. So for example, here is calcium 8498. And then the satellite lines, just put the index behind in any order. So I can put here 8 and then at the end 5. It doesn't matter because the code will just read all those index and then just put them inside this spectral range. But the important thing is that the spectral range is always referred to the calcium line. Okay. Did I say it? Okay. Did you follow me? I hope. Okay.
Yes.
Yes,
Okay.
yeah.
Thank you. Thank you. So then this is basically what I say here. I'm sorry, I'm losing my voice slowly. So we repeat the same, exactly the same. So we read index 1 for the first blend of 2 iron lines. Then now it's also easier because we are reading index 3 for the blend with the calcium line and all the other lines, and the same index 4, and we are reading the calcium line plus all the satellite lines. Okay, and we do the same plot. I just changing the label, so later on you can compare them. And I'm making a bit wider the wavelength range because in the previous plot I wanted to focus on the core of the line, but now I want to show you how the spectral range looks like. Okay, so then in this case 8498 looks like this. Okay, so we are getting here there's an iron line that is very sensitive to the magnetic field. I think it's the factor 1.75 or something like that. And then we have additional lines here that are relatively strong. But the idea is that both with, for example, Visp on the Kist and Skip on Sunrise, you will have this full spectrum. So the best thing you can do is to fit the calcium line plus the other lines, because you are better fitting the different things that appear there, because this, if you don't tell the code that this is another line, the code may try to fit this as a huge gradient with a second component or something like that. But if you tell the code that this is a line, it said, oh, okay, now it's made my life easier. So then You are simplifying the synthesis, sorry, the inversion process, but also you are providing more information to the code, because you are providing valuable information to better constrain the atmospheric parameters. Okay, and in fact, if you see the polarization signals, this line, even if it's located in the wing and is affected by the opacity of the calcium line, is still producing larger polarization signals in the 3 Stokes parameters. So then having this line included in your file when you are inverting the calcium line with a spectrograph type data, it's going to be very helpful, because you can see that in the Stokes B, it's very close to the wing, or sometimes it can affect the shape of the calcium line polarization signals. So I think it looks very nice. Okay, and now let's check for the 8542, and then again this is the same. So we have a few lines. Calcium 8542 is so broad that they look tiny, but they are reasonable lines, but it's just the line is really broad. And we have now 2 lines. Oh, sorry, I forgot to mention, so let's go back. So in the case of 8542, okay, it's index 4. So we have that this is 536, 538. So then we have 2 lines in the blue wing of calcium 8542, and then 548, 548, and 550. So we have 3 lines in the red wing of the calcium 8542 line. And this is what we have here. So 2 lines in the blue wing and 3 lines in the red wing. Okay. And then the signals, you can see they are, in fact, they look very different to the calcium line, probably because they are seeing the magnetic field in a different way. And also the temperature is different between the formation or the region where the line core is sensitive in both cases, in calcium and photospheric lines. And then in this case, as the lines are relatively weak and they are also not so sensitive to the magnetic field, we have comparable amplitude in the Stokes profiles, although we also have a gradient. So probably with a constant magnetic field, this may be different, but maybe this is closer to what we have in the sun. So just to give you an idea that if you're observing the full spectrum, it's good to have also the satellite lines included in your inversion configuration. Okay, so now we are going to compare a normal atmosphere with the atlas, and using this exact configuration. So we are not changing now the synthesis configuration, just the input atmosphere. So is there any question before we go to that point? Okay, no, thank you. Okay, so then let's go to day round 4. This is the last one. So okay, I open this one. Let me close all this one because we don't need them right now. So then I'm writing here a lot. You know that I like to talk and to write. But essentially what I'm saying here is that I think this exercise is an illustrative one because we are showing you how to do different things, but it's also a pragmatic one because those of you that plan to use the keys, and I hope it's everyone, will have access to this type of spectral windows very soon. Maybe if you are included in the first call for proposals, maybe when the data start to get released. So you will have access to exactly this window. So then we are paving the road for embedding this data. And the same for Sunrise. Those of you who are going to use Sunrise data either this year or eventually, you will have these exact wavelength regions to fit, except the iron one in 630 nanometers, but the 2 calcium lines plus the satellite lines, you will have access to them. So it's an exercise that I think is very helpful. So, but we want to compare with a normal atmosphere, how they look compared to the atlas. So then in that sense, if you remember, I recommended you to use this atlas. I like it, it's very dynamic. So just go to, for example, 8542, then right here, Magen 10. Well, sometimes it loads, it doesn't load, but when it loads, just click here in this button, and then you will have the data here and you can download it. Okay, so just type here the wavelength range that you want to use, and then if it works, let's try to reload. And then in this button, you can download the wavelength and intensity, and you can make any plot. I will leave it for now, but trust me, it works because I did it the other day. And then what I did is I picked 3 different atlas, so at 630. So you have here wavelength and then intensity. And then I did the same for 8498 and 8542. Okay. So then what we're going to do now is we are going to take the HSRA atmosphere, but this time we are going to keep it as the original one. Okay, so then the microturbulence in the original model is 0, so I'm just keeping it as 0. But magnetic field strength, I'm sorry, magnetic field strength, velocity, and inclination and azimuth, they should also be 0, because in the original model they were 0. And then we are writing this as our initial atmosphere. We run the synthesis with the same configuration as before. And now we can plot the profiles that we synthesize versus the atlas. Okay, but the atlas is on intensity, and we are also using a model that it has no magnetic field. So then we are going to compare only intensity profiles. Okay, so then this plot is the same as before. So it's a Stokes I, and then I'm adding the atlas and the Stokes I. I just put it here, no data, because I wanted to put it in red color to allow you to distinguish the 2 lines better. And then I just add in titles. So let's see how it looks. And then, okay, so this is what we have. Just one second, sorry, I forgot. So if you download the data from BAS 2000 database, it will say that the continuum of each wavelength region is normalized locally to 10,000. Okay, so in principle, to have everything normalized to the local continuum as we have with DeSIRe, just divide everything by 10,000. Okay, so then the black line is the atlas that I divided by 10,000. It's not exactly 1, so I don't know if we may need to adjust this a bit, but this is a very quick comparison, so we may not need to do that. But just as a reference, the red one, that is the one we synthesize, is 1, the continuum, but the black one is a bit lower. Maybe we need to update this a bit, but just for this example is probably fine. So then black atlas, red the synthesis, and you can see that we have 2 lines and they are okay. So width, it looks fine, and line core is also looks fine. Later on, I will explain why you may see difference here, but for now, if I see this, I will say, okay, it looks fine. So the atomic parameters for those lines are probably okay. Then let's do the same for 8498. And this looks very nice as well. So we have that, again, the continuum is not exactly the same, but it's probably, I would say probably okay. And then the width of the line looks also fine. The line is again a bit deeper than the atlas, and here also a bit narrower, but I will explain later why we may have these things. And then we have this strong line that again is also deeper, and then these 3 here, but they are lines that you notice when you see the line. So for this reason, we decided to include them in the lines file for future inversions, because you may want to fit all these small lines, but this could be maybe extra work and maybe will not provide so much information. But these 3 are big ones, and also this one. So maybe probably with these 5 total lines, I think you are fitting this spectral range with high accuracy. Okay, and then let's do the same with 8542. So again, the range is very, very broad, but it seems that again we are really getting close to the atlas, the width of the line. These lines are a bit deeper, but again they look similar. This one also looks very nice, and these 2. So if I see this, I would say it looks fine. I think we are probably selecting the correct spectral line, because sometimes you can make a mistake because they are several spectral lines that are together, and one that you think is the correct one is not the strongest one. So I would say that they are probably okay. And also we are using the most accurate approximation for the coupling. So we are using in some cases LS coupling. I forgot to mention that, sorry. We are using, this is part of next class. I will say it later, but next class. So in this case, we are using LS coupling. So this is 2s plus 1 is the first index. P is the the angular momentum. And then 2 is the total angular momentum, J. So in this case is LS coupling. But then here we have JJ coupling for the upper levels. And then in this case, we have JK coupling. So with this line example, we are going to cover the 3 possibilities that you can have in DeSIRe. So, well, yeah, in DeSIRe. So then in the next class, we will very quickly cover again how you can provide the information of a level that is not LS coupling. So we will make this example and probably this one. So then you can have an example that you can use for later on if you want to add lines. Okay, so then I was saying, I think it's probably fine. And there are some differences. Just let me explain what things can make those differences from the atmosphere that we are using. And then also some difference could be that the atomic parameters are not strictly correct. But we also have to bear in mind that the HSRA is a relatively old model, and it was not devised for really reproducing the narrow window that we are using for comparing. It was for reproducing different things. Also, it doesn't contain microturbulence correction. So if you go, so HSRA is from the 70s. So if you go to models from the 90s, like the FAL models, they have microturbulence correction. So chromospheric lines, they look much better. The line core is much wider. So those things that we saw as a narrow line core region, probably with a microturbulence correction like the one we have, the FAL models, it will be much lower, the differences. And also we don't have macroturbulence correction. I think in the case of the Atlas, probably we don't need it, but with different instruments, you sometimes need to add an additional enhancement that comes from limitations in the spatial resolution, spectral resolution, and other things of the instrument. So in the case of a spectral resolution, if you don't have the accurate point spread function of the instrument, what we usually do is to add a microturbulence that is applying a correction with a Gaussian shape that is trying to replace the point spread function that you would have if the instrument would provide you. And this usually enhance the line and reduce a bit line core intensity. So there are some things that in the inversion you may add if you don't have information from the instrument that will make things a bit more accurate, and we don't include it. We didn't include it in this case. So I just wanted to have a relative relation, but there are a lot of things that we may include if you want to really have a synthesis that is really close to the Atlas. So this was just to have an idea if the atomic parameters and the lines and the coupling configuration that we were using were providing reasonable results. Okay, so then this means for me that we are just a step closer for getting our hands on the keys and sunrise observations that we'll have probably in a few months from now. So for me, I'm very excited. So I hope you are as well. So, okay, so then I will go to the presentation, back to the presentation, to homework. But is there any question that you have related to this file or to the previous one?
Carlos, yes.
Yeah.
So I had some quick run for the codes you provided, and I could not find that LPR file .pro routine, you know, the one which you are using for reading those .per files.
Okay, so let me check. So in online course, I have a folder. I think I'm always sharing this folder with you, right? So when you click the link, you go to this main folder, right?
Yes.
So then it should be here. So this one is the same or not? Let me see. Maybe I change the name. Let me see. Yeah, so the one I'm using, this one, it's here in the online course main folder. So you have RH, SER, DeSIRe. So we are now in day 3. But if you go back, then you have a folder called ideal procedures. And then here is the routine that I'm using for reading the profiles.
Oh, okay. Okay.
In principle, yes. So in principle, I try to put all the routines that I use there. But if someone is missing, just let me know, because maybe I forget. But this one is there. And I think also I'm using write mode. This one is also this one. Okay. And
okay.
also read mode should be there also. Yes, this one. Okay. So then in principle, when you click the link that I usually send to you, you should be here. And then there's an ideal procedure folder. And hopefully when Ricardo finds some time, we will also have a Python procedure folder there. Okay, but in principle, all the routines that I use, I always try to put them in there. Okay.
Okay, thank you.
Yeah, thank you. Okay, so then we are back to this side and day 3, okay? And then we go back to the presentation. Yes, so as always, I just recommend you to try to examine all the examples I presented in the class. So today we had 3 different ones, so only iron lines in the visible range, iron lines plus calcium lines in non-NLTE, and then iron lines in the visible range plus calcium plus satellite lines in the infrared. So try to run these 3 examples. For me, the important thing is try to see the difference between one and the other, because if you really understand what you are changing from a non-NLTE to a non-NLTE computation, I think it will be easier for the future to really always have an idea if something is wrong or something is not working, to start checking, oh, am I running the atom in non-NLTE? Am I running the lines that I want to solve, or I'm mixing index or something like that? So I think just going through the exercise probably will help you to have an idea, or to even make a checklist of things that you want to check every time that you're going to run synthesis or inversions. Okay. So then, and just this is a comment, we will go through the transitions next week, but I think it's always good if you want, and if you have time and you want to check the atomic information of the lines that we included, it would be good if you check it and you said, oh, I double check and they are okay, because sometimes when you are preparing large number of line files, you can make a mistake. You can mix a J value from one transition to the other. So if you see that there's a typo, just let me know. And if not, we will trust me for the future. But it's always good. If someone has time, maybe just check it. You don't need to do it now, but eventually, because it's always good to have a different pair of eyes checking these things. Okay. So then next class, we will combine 2 things. The first one is what I said. So in the SER class, we learn how to prepare the line file. We learn how to compute the enhancement factors due to collisions with neutral hydrogen. Then in the RH class, we learn how to compute, or how to provide the information for a JJ, a coupling, and for a JK. And the idea is that the format is the same, because we developed that update together. So the format we use for SER and RH is the same. So I mean, DeSIRe and RH is the same. But I would like to spend at least 30 minutes just double checking, taking one example, revising how we did it, so then you can have a real correlation. And then I think the last part of the class, probably 20, 25 minutes, we will compute response functions with the same configuration we had at the end. So iron lines in the visible, and then a combination of non-LTE and LTE lines in the infrared, compute response functions very quickly, very easy, just maybe temperature, magnetic field, and velocity, just something simple, but just to allow you to revise that is the same procedure as DeSIRe, but just to have an example of how to do it. Okay, so then this will be in 2 weeks from now on March 11th. I hope my voice will be better by that time, hopefully. So before wishing you a nice weekend, do you have any last question? Okay, so if not, enjoy the weekend and I hope to see you in 2 weeks. Thanks a lot.
Thank
Bye.
you.
Thanks very much.
Thank you.
Bye.
Bye-bye.
See you. Bye.
Bye-bye.
Bye.